Hey, this is Alex from Gretel. Today I'm going to walk through a topic that has been super popular with our users, and it is how to generate differentially private synthetic text using Gretel GPT. So at those times where you're creating a training set for an LLM or a RAG-based system and you need to have privacy guarantees, you really need to go a step beyond what traditional de-identification, like removing or replacing names or addresses, into something you can have guarantees that no other attributes inside of a text sequence, like for example, a reference to earthquake related delays or things like that, and plus a username could be used to identify a user. So differential privacy gives you actual guarantees that the model cannot memorize or replay data at an individual level. So let's go in and talk about how that works, and we'll walk through a practical example here. So I'm going to jump right down to the bottom of the blog. We have a couple data sets here, one on clinical notes and the other on a dialogue-based system, very similar to what a lot of people train on, where we have configs and data sets, which are linked to the video that you can try running yourself. So we're going to run through the full kind of process for the augmented clinical notes right now. If you go over to the Gretel console, I am going to first, we'll look at these pre-trained models, but I'm going to go ahead and walk through the full process of starting off the fine-tuning using DP. So here we're going to click on the blueprint for generate natural language, select the blueprint. I've already uploaded the data sets to a project here called DP Synthetic Text. So we're going to go ahead and use that. I'm going to select the clinical notes. We'll start with that training. And here we're going to edit the config. I'm going to take the config that I grabbed from the previous tab, copy it, use that to replace this config and look at some of the changes. So we're still fine-tuning the Mistral 7 billion instruct model. I changed the text name, so the column name we're going to be fine-tuning on is just called text. You see other parameters here, including the DP where you set the epsilon. Delta can automatically be calculated, and we're going to generate 80 records and then compare that versus the real-world data to compute our synthetic quality score. So I'm going to click run. What's happening in the background here is, as you can see, it's about 30,000 records that we're training on. It is firing up a container, which will fine-tune the Mistral model using Gretel's DP implementation, and then create a synthetic quality score for it at the end, let you know how good of a job it did at learning the distribution of this data set. So it's starting right now. You can see the model kind of going through. Let's go over to the models examples that we've already run and walk through this. So here I'm going to jump over to models. Let's look at the clinical notes once again here. So you can see this training actually for 30,000 records using this config took about 9 hours. The quality score was a 76 out of 100. We'll dive into what that means right here. We're using a very high level of privacy. So if you were to set down the epsilon to 13, 15, things like that, you would get very close to real world results. With a 5, which gives you really strong guarantees, you're going to have a little bit of reduction in quality, especially with only 30,000 records working with. Now let's dive in and look right at it. So here you can see the training starting and essentially firing up and training on the data. One of the questions we get a lot is, how does synthetic text look like when compared to the real world data? So let's start by just looking at the real world data. So I can go back to the main screen here. I can see the data source. So I'm going to go ahead and download that. It'll take a second to download. That's about 100 megs. And then let's open this up and take a look. So here I'm opening it up in a spreadsheet viewer. It should be good enough to get a feel for what the data looks like. So here you see a set of clinical notes here, right? A 32-year-old person with a set of conditions or things like that. So here you get kind of this very specific, very domain kind of oriented language talking about symptoms that people came in with. So the question is, what does a synthetic text look like in comparison to that? So let's go ahead. Next, we'll take a look at the actual synthetic text that was generated, and then we'll look at the quality report. So first, we'll eyeball the results of these 80 records that were generated and make sure that it looks kind of meets our expectations for the data. So we're downloading the results now. Give it just a second. And I'll open up. Here's the synthetically generated text. So here you see something that looks an awful lot like our original data. So it appeared to have learned the domain of the underlying data very well and is reproducing records here that really match kind of at least the visual test for the semantics of the original data it was trained on. So looking good so far. We can see here a 60-year-old male patient was admitted to the thoracic surgery department with a lung tumor. So it all makes sense here. Heavy smoker. So you see the data being very correlated. The idea here is that none of these point to a real individual from the real world data set. But the aggregate, if you were to query this or look at any of these records in an individual basis, would be very interesting and useful for downstream ML training, for data sharing or things like that. So pretty cool capability. Now let's go ahead and look at the quality report. So we generated synthetic text with differential privacy guarantees for all these clinical notes. How does it compare to the real world data? So we can see here for this example, the 2 dimensions we measure on are text semantics. So how similar was the text? We use an embeddings model. As you can see here, it supports over 50 languages to compute this metric. And then how similar was the structure of the text to the original real world data? And this is a little bit lower. So we're going to want to kind of really understand what that means. You can see it really here, actually. So you can see that in the synthetic data, it used a few less words per sentence, a few less characters per word, and a little bit less sentences than the original training data. So we can adjust really inference parameters to account for a lot of this stuff. So we can raise the temperature, raise the max tokens, things like that. Also increase the input data you're training on. But here we can see the actual text semantics look very good. So here you see the distributions and our PCA plot matching very closely. And then here you see kind of a visual distribution of the structure areas where sentence count a little bit lower on the synthetic data versus the real world data, but in the same ballpark. Similar words per sentence, a little bit lower, but still useful. So here's a case where we have put together a model that can be used to sample unlimited synthetic data. You can use this to train a model that looks just like the original real world data was based on, but we have that differential privacy guarantee that it cannot be linked back to the individual is based on. So this makes it awesome for training chatbots, creating training or fine-tuning LLMs on very domain-specific data, things like that, where you want the insights. Essentially, you want the models to learn about the disease without learning about the patient. Please follow along. Let us know if you guys have any questions, and we'll look forward to hearing back. Thanks.